Okay, we're back. So all I did is I erased that 7 and equivalent that I had there, and I put it here. And I didn't put the value of the voltage. There I had it labeled as the open circuit voltage. I'm going to solve for that open circuit voltage, and that will be the value of this voltage source. And then I'll find the 7 in resistance by also getting the short circuit current and calculating it and putting it there. And then once I have that, I've got my standard first order circuit, and I can just go plug into the formulas. So I need to find the 7 in equivalent. All right, well, finding the 7 in equivalent means first, well, there's a couple different ways to find the 7 in equivalent. If you only have independent sources and no op-amps or dependent sources, then you could do it by just looking at the circuit from the perspective of the terminals A, B, and then killing all the sources. But we don't have that. So we have to find the 7 in equivalent resistance by first finding the open circuit voltage, which will be the value of this voltage source, and then finding the short circuit current and doing the calculation of open circuit voltage divided by short circuit current. Okay, so first we're going to find the open circuit voltage. So to find the open circuit voltage, I'm going to use picture or figure A. This is kind of important because, and I'm going to, you would actually be required to redraw it on your paper, but because of the space limitations and also the time limitations, I'm going to go ahead and label this figure A, and I'm going to change it just a bit. Because remember, I'm looking for the open circuit voltage, which means that I'm looking at it from the perspective of A and B and opening up those terminals and labeling a voltage there, VOC. That's what I'm looking for, is that open circuit voltage. All right, so then we can just do an analysis of this problem to find VOC. And actually, we can almost do this just by inspection. Here's how. I have a current going here. Let's just call it I. When it reaches this node, it can't go this way, right? Because it's an ideal op-amp. And remember, an ideal op-amp, this current is 0. It can't go this way because that's just an open circuit. There's no place for it to go. So this current here has to be the current here as well. And then if we look at this node here, again, this is 0 because it's going into the non-inverting node of the op-amp. So, okay, and this, again, I mean, this is just going backwards. This is I. That means this has to be I. So the point is that the voltage between here and here has to be the same as the voltage between here and here. Okay, I forgot to label some of the node voltages. Okay, this is the ground, right? So this is 0 volts. I'm using the idea that this is an ideal op-amp. The voltage in the non-inverting node has to be the same as at the inverting node, so this is also 0 volts. So obviously then this is a 0 voltage node here. This node here is 10 volts. So what's the voltage drop across this resistor? It's 10 volts. Look, 10 volts here, 0 volts here, so the voltage drop here is 10 volts. So you've got the same resistor, the same current. What's the voltage drop here? It's got to be the same. So this is also a 10 volt voltage drop. So VOC is equal to 10 volts. All right, so now I know what this is. 10 volts. So I'm halfway done. Okay, so now, so I've used figure A to find VOC. Now I'm going to use figure B to find ISC. And maybe just because you're going to have to do it, I'll go ahead and redraw the picture too. Because this one's such a mess, I don't want to just erase. Okay, so when I'm looking for the short circuit current, I realized I want a little bit more room there. Okay, from the perspective of A and B. Okay, so that means A and B gets shorted out. Okay, so there's the picture. So we know this is 10 volts. Yeah, because of this picture. 20 kilo ohms. These are all 20 kilo ohms. 20 kilo ohms. And this is the ground. Okay, so there's the picture. Here is the short circuit current, ISC, right? This is terminals A and B. That's how you find the value equivalent, is that you short it out and you find that short circuit current. Okay, so let's do that problem. So we're using figure B, okay, label it, figure B, to find the short circuit current. We've got this short in parallel with this resistor, so that actually shorts out the resistor. It's figure B here. So this resistor is shorted out. All right, so we've got, let's label this current I again, like we did here. And so I is ISC, right? Yeah, so this is like collapsed, right? The short circuit current is just the current that's going, you know, the terminal A and B, it's now the same as what was going through across that resistor. So we've got I, you know, it looks too confusing to have both of them there, so I'm just going to erase that and just, okay, so here's the path. And we've got it going, and so the I is going to go, so I is equal to ISC. And what is it? Remember, this is 0, so if we just do Kirchhoff's current law around this perimeter, we've basically got, what's current law? We've got minus 10 volts plus 20 Ki plus 20 K ISC, but of course ISC and I are now the same thing because there's no other way for I to go other than up here, because remember this is going into the OpAmp, so it's 0. So these are both the same current, so I'm just going to call it, actually I might as well call it ISC because that's what I'm looking for. So I'm just going to change this name to ISC. And then equals 0. So solving for ISC, you get 10 over 40K. So what is that? 0.25 milliamps. 0.25 milli. So there's ISC. All right, great. So now that we found ISC, we know that RTH is, well, let me just put it here for now, is the VOC, which was 10 volts, over 0.25 milliamps, which gives us 40 kilo ohms. Okay, so we found RTH, 40 kilo ohms. All right, there's our first order, our standard first order circuit. The rest is just plug and chug into the formula for a standard first order circuit. Remember what it looks like? Anybody have it memorized? Of course, it's an open note, open book test, so you don't have to memorize it. I have it. I remember this formula. Remember this? There it is. Oh, by the way, I'm finding VC. You were actually asked to find V0 here. What's the relationship between VC and V0? Look, remember, this is ground, so this is 0 volts, this is 0 volts. I mean, this is essentially the ground. So the voltage, right, V0, this is the node voltage V0, this is ground. So V0, if I wanted to show a picture of it, would look like this. So look, between the same two nodes, this is labeled plus V0 minus. This is minus VC plus. So the bottom line is V, and I should have said this at the very beginning, V0 is equal to minus VC. So once we find VC, we've got the answer to the question that's being asked. So that's why I'm looking for VC, and I should have said that way earlier. Okay, so once we find VC, we've got what we've been looking for. X is VC, because for our standard circuit, you know, it has a capacitor, so what we're looking for is the capacitor voltage. So VC is equal to, okay, the voltage at infinity. Remember, you can just look at that quickly by saying, okay, it's a constant source. Capacitor acts as an open circuit to a constant source, so there's no current through here, so the voltage is 10 after a long time. So 10 volts plus, and then the initial, remember we found that, is 0 volts, 0 minus 10 again, e to the minus t over tau. What's tau? Tau is RC, R is 40K, C, oh I had forgotten to label it, but I stuck it in there during one of those breaks. The capacitor, capacitance is 4 microfarads, so that's 4 micro. So the final, okay, so the answer for the capacitor voltage is 10 volts minus 10 e to the minus t over 160 milli, because 10 to the third times 10 to the minus 6 is 10 to the minus third, so that's where that milli comes from. And so V0 is the negative of that, so it's minus 10 volts plus 10 e to the minus 6.25 t. Because if you take the reciprocal of 100, you know, it's really 0.160, right? And so you take the reciprocal and you get minus 6.25 t. There's my final answer.